What is up, team? It is your boy, the Canologist. We are going to be doing another Leetcode problem. Minimum depth of a binary tree. Right, so let's get into it. I've never done this type of question before, so I'm going to try and attempt this for 15 minutes, and then if I can't get to a solution, what I'm going to do next is start looking at resources to solve this. All right, and I'm gonna try and avoid using ChatGPT unless I have to. It's like I want to kind of like get something out of my experience of this new problem. Minimum depth of a binary tree. Given a binary tree, find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. Remember, that is the number of nodes along the shortest path. The root node to the nearest leaf node. So that'd be this, I guess 3 and 9. A leaf node is a node with no children. Okay, so 3 and 9. The other leaf nodes are 15 and 7, which look longer. Number of nodes of the tree could be 0. Okay. The value of the node could be negative 10. Okay, so the value doesn't really matter. We care about the depth of this tree. So right now we know here by the constraint, the tree's nodes range from 0 to 10 to the 5. So you could have 0 nodes. So I guess my first step is going to be if roots return 0. A root is the, okay, yeah, so right now they're going 3 is the root. So they're representing the tree with root with this array. So that's like not the actual thing you're supposed to be looking at. But for argument's sake, yeah, so this is like 3, 9. And then null, null, so that's the left side, and then the right subtree. You see what I'm saying? So if root equals null, so none, I'll return 0, because all we care about is the length. Okay, what next? Let's see if we can kind of map it out on the whiteboard. The minimum depth, number of nodes along the shortest path of the root node down to the nearest leaf node. I could also create a function to get the shortest length. Okay, so let's open up the whiteboard. Whiteboard online. Add your object first. Okay, so I got a pen, so I'm gonna create a circle here. Let's recreate that tree. Circle here, here, here. Okay. 3, 9, 20, 15, 7. So 3, 9, 15. Oh, 20, 15, 7. Okay. I should have made these nodes bigger. Actually, I could. Let me see if I can undo. Okay, 3, 9, 20, 15, 7. Okay, so these are our blobs, aka our nodes. Now I'm going to go to each one and draw this. Okay, so now I have some sort of tree linkage. All right, so how do I find the shortest path? If I was to look at this node, my first thing would be I got to traverse it somehow. So I look at my node left, out, right. So if node left is none and node right, so if node left, let's put NL equals null. Is that the case? And if so, we now know our shortest path. Oh, from the root node to a leaf node. If null, if node to the right. So this is null. Let's say this didn't exist, right? Scribble that out. It's just 3. This wouldn't be a shortest path because there's no leaf node, right? This is the root node. The leaf node would be 15 and 7. Right now we have 9. So right now we would check if the node left is null and the node right is null. Shortest path is 0. Right, so and the other thing is if one of them is null, you have to go to the next one. So if node.left is null and node.right is null, then you want to return length. If node.right, so if both are null, you want to return length. So if node.right is null. So if both of these are the case, I want to return the length. Oh, len. Okay, then we're done. Right? If one of these are null, just delete the scribble. Oh shit, I could turn this into an eraser. That is useful to know. Okay, and I'm gonna stick with my pen. So right now, if both are null, then we know to return the length because right away, like there's nothing more to traverse, right? And if we do hit null, like let's say we hit 9, for example, both nodes are null, we return the length. This means that we're at a leaf node, right? And if we're at the root node and there's nothing there, we just return 0. So we have a base case for 0. And then if it's not 0, we have a base length of 1. Because if we look here, 1, 2, the minimum depth of nodes along the shortest path from the root node down to the nearest leaf node. So 1, 2. The number of nodes. The minimum depth is the number of nodes. Okay. So that would actually mean if root is none, return 1. Because at minimum, you can have 1 length. Or no, if the root doesn't exist, so you can have number of nodes in the trees from 0 to 1. So if root equals none, return 0. So at this point, now I could say our base case is handled. If there's no root node, it's going to be 0. If there is a new root node, at minimum, the number of nodes is 1. So your length isn't the number of vertices, no. it's your number of nodes. So right here, this would have been 1, 2, 3 if you go to 17. 1, 2, 3 if you go to 15. So this is 3. And then 1, 2 if we follow this. So this is just logically tracing out where I can go. How much time have I gone in? All right, I'm already 10 minutes in. So let's start getting to how to solve. So basically, if both are null, return the length. Otherwise, if node left, traverse, and then if node right, traverse. So basically what I'm doing is I'm doing a traversal. I'm going to traverse until I find a leaf node. And this is what this above context is for. Then I can return that length, and then I will get, at the very least, I'll get, what's it called? The minimum length back. Right, so if both are null, I return the length. So I'm going to go, okay, number 3, I want to traverse left. Is there a node dot left? Yes. So now I return my node dot left. All right. My length is already 1. Now I add 1 to the length, and then node is 2. So now it's going to go if node dot left and node dot right are null. Yes. So that means since they're both null, it's going to return the length. So now we're out of that function. And once we're out of that function, we go back to the original function and we return the length there to solve the problem. So now this tells us that we found a leaf node. We return the position of that leaf node, so 2 nodes away from the root node, because the length increases by 1. And we give that length back to the original function and return to get the answer. So now I'm going to go def find leaf node length or position. So I'm going to say pause. Find leaf node pause. So find leaf node position, and this is going to take a node and a length. Let's see if we can make it a part of the function. If we make it a part of the function, then I have to add self, because we're going to be referring to itself. So let's go back to our whiteboard, check our logic. Let's see if that works. If node dot left, and node dot right equals none, we found a leaf node. So return, let's just call this L, because we don't want to mix it up. With this, we don't want to mix up L. Right away, also, if we know there's no root node, return 0. If there is root node, we start off by returning 1. So I'm going to say length or final. So I'm going to say return L. Return the value of L, right? The other thing is Found the position of the leaf node. Okay. The other thing is, so final. Now we want to take the answer and bring it back. So we want to take our returned answer, bring it back. So we gotta go self dot find. We're gonna link this function back to the original function. So find leaf node pause. So now I'm gonna add in. So self is already a thing. So I'm gonna add the node root. I'm gonna add length equals So let's go back to Python again. So Python default values. In Python function, that's what it's called. Default arguments, parameter equals default 3, so equals fifth, equals mark equals standard. Okay, so all I could do here is L equals 1. I give it the default of 1 because it's already passed this if check for 0. So anything now, it will return at least 1. And then return final. So I just want the length value. No dot left and no dot right, so then I will go find leaf node position. I don't think I have to do it within itself. I only have to do it within another function. Can you call a function within itself? Yes. So I'm going to do here. I might have to use self. I'm just curious. And then I'll put the node value in here and L plus 1. L plus 1. Then I'm going to traverse the right side to see. So if there's no node on the left. If there's no node on the left, then traverse the right. Find leaf node pause, node L plus 1. Okay. So basically what I'm doing now is I have my function, I check if there is a root, if not, return 0. If there is a root, return 1 at minimum. And then traverse to find the nearest leaf node. So I have to go into a function, and then I return that into final. So this function here checks to see where I find the nearest leaf node, return that length that we're saving here, and then pass that back to the final, return the final. Let's run it. See what syntax errors come up. It's not defined. Okay, so we got to use self within itself. So self dot run. No dot left, no dot right. Maximum recursion exceeded. Why? Oh, because I'm re-traversing the same node, so it's continually looping. It's continually looping because I didn't traverse. So no dot left, I have to feed it no dot right. I mean no dot left. Because now it's like repeating, going on the same node and just adding length. No dot right. If no dot left, traverse no dot left, add 1. And then no dot right, add 1 until it hits a leaf node. So this is another thing to check for. Okay, none is not valid for the return type. No dot right, no dot left, find leaf, no pause. None is not a valid value. Type error, root. So the actual values of the nodes don't matter. We're just looking for the nearest leaf node. Line 51, line 45 of the driver. Expected return type is integer. Final. Return L. L equals 1. Or return 0. So at base it's 1. Otherwise, it's going to be 0. If you have a root node, return that. So final. Or I can find the max length here. If no dot left, return. So I could say left, right, and then return the length that's longer or shorter. Because there will be other leaf nodes. So if no dot left, if there's a left node, go left, otherwise go right. And then if no dot left equals none and no dot right equals none, return L. Where am I going wrong? What's my time at? I'm at 24 minutes. Okay, so I have to figure out how to solve this now. Minimum depth, find like node. Why is it not working? So according to my logic, everything looks okay. Maybe there's a way I'm not doing it correctly. So let us now use ChatGPT. Dynamic tab change. Okay, so we have to find left and right. and then if left, right. So, okay, so it basically takes what I'm doing one step further, and all it does is have the right idea, but you have to have return left and right depth. So left depth equals, let's see what they do, negative infinity, float inf, initialize with a large number, if node left depth, self dot node, if node right, okay, right dot node, and then left depth, right depth. So we're finding out which one is it's going to traverse either one. We want to find out which position is shorter between the two. So it looks like you're trying to find the minimum depth of arrays, binary rows. There's a small issue, and you're not method where you're not returning the recursive calls when traversing left or right subtree. It's a corrective version of code. So all I have to do is initialize some number here. Oh, and they use infinity because that's the greatest it could possibly be. So float inf. So basically, guaranteed, it's just always going to return the lowest number. Let's say float right is none. It's going to be an infinity. So by default, it's going to be the left value. So what I'm doing here is all I have to do is this. Just take what I did because I was going to traverse left and right. So all I have to do is return this value. So I got to go left. Left underscore depth equals, and then wait, let's correct the indent. Right underscore depth. So basically what it's doing is I'm gonna return the length as it traverses all the way down. So go left, right, left, right, left, right, left, right, right. It's gonna go left. So basically I'm checking the left subtree if it's there, right? And that will already include this. So it teleports. So when I say teleports, it goes to the final answer. So let's say there's no dot left. Let's go left, right, left, right, left, right, left, right, and return that value to no dot left, right? And then let's say we pass no dot left. Now we go to the right node. Left, 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 left. So basically what it's doing here is checking. At the beginning, it's checking if where the leaf node is, right? This is my base case. Find a leaf node, return the length, right? What these infinities are for are basically saying whatever the minimum length is after that point. You have to have a leaf node. So we sent the root in, so that's 3 right here. Now we have 9 and 20, right? So 9 and 20 have a depth of infinity right now because we're trying to find the minimum length that they can be. So right now we're going to return you have to return this value. So this terminates where the traversal goes. Right, but we have to bring that back to these values here. So what this does is basically it's going to go min, left, left depth, right. I put right here. Right depth. So basically this is my updated solution. So it takes the minimum of both. So basically now I get 3. So I start at 3. Now I go 9, 20, right? Now if there's no nodes, return the length, right? So it goes back, it returns as it just returns L. the base case gets met, right? So it returns L, we come back, we get a 1. Final is 1, right? So if it's not, now we have left and right float nodes, right? So L is 1 currently. If there's a left node, right, we're going to traverse that. So boom, L is now 1, right? And let's say it ends here. So 9 ends here, right? Now it's going to return L. So this float dot left is going to be 1. Now there's going to be, we're going to check if there's a right node, right? So right node is 20. So we go 20. We traverse into that. Now we go back to left node, right node. So left node, 15, right? So we're at 20. We traversed again. L is now 2. At 15, we return that. So 2 is greater than whatever's on the... Now it's going to be, because now we're at 15. The length is at 2. Node dot left and node dot right are both 0. I mean none. So we return the length. So 2 comes back. So now it's back at 20. So this left node is explored at 20. So you have a length of 2. Now we go to the right node, 7. Right? So it's going to do the same thing. 7's at position 2. Min dot left, min dot right is it's going to be 2 and 2. So now we go back again, because now it recurses back. You have to go back. So we did 9 and 20. So 9 is going to be 1. 20 and 20 is 2. So that returns 2, the minimum of both. And when we compare that, we return 1. Because 1, the minimum compares left and right. So we now have the left and the right from back when 3 passed down these 2 nodes. So right now we did 9, explored 9, 2 explored 20, explored that, right? It returns their values. So 20 had 2 as its max path going down, 9 had 1, right? So now it's going to return the minimum of both. So 1 is less than 2, it's going to return 1. We return the final. Let's run that. Boom. And let's submit that. Boom. And it beats 5.8%. So basically, once again, minimum depth. All I want to do is check. So like we did in the whiteboard, you could pretty much flesh out your idea on the whiteboard. Most of the solutions to these easier problems are basically you visualize the problem on a whiteboard like this. And then basically, how would I solve this problem? Like, fuck the code right now. Forget anything about code. How would I solve this problem if someone just showed it to me on paper like this? So it's pretty much what I would do. Just go here, compare. Okay, there's nothing here. Okay, so I checked my base case. That's why I created my base case here. Then if there's a node dot left, if there's a node dot right. See, I didn't even follow my own advice. See, look, if I go back to my function, I originally just did this. If node dot left, then node dot right. And then just traverse right? I just assumed it would be there, right? But if I followed my own advice here, I would have had 2 traversals of left and right. And then you return the minimum of those traversals, right? And then this return value basically lets you pass it up, lets you make a comparison. So this is your base case that you want to return off the bat, or from recursions, this is the value, this return value is what you give back to your function that made the call. That's an important distinction. So that's how you solve minimum depth of a binary tree. If you like this video, please give it a thumbs up. Please leave your comments. If you'd like to see anything specific, let me know. And yeah, we'll keep banging these out. Knologist out.